We have a very short exploration here, 3.5. We are going to be, well, let me say this. In the previous exploration, we dealt with the distributive property, and we talked about how that is a legitimate simplification or a legitimate manipulation of expressions that we can do. You can distribute multiplication over a set of parentheses with things that are added or subtracted inside. Um, the thing is, there's lots of other simplifications or algebraic things that people do that aren't necessarily correct. And so that's a little bit of what we're looking at here today. Okay, so in mathematics, a thing called a counterexample is a specific set of values or a specific example that shows that something doesn't work. All right, and we're going to be seeing lots of counter examples in this exploration in particular. All right, um, all right, so on we go. We'll keep using that word a few places here and there. Okay, so down here is a table just full of a bunch of expressions to compute. You can clearly see how they're related across the rows. I'm going to pause the recording and fill them out. You try them, get those guys all computed, and see what happens with them. All right? All right. Okay. I filled all mine out. Um, Clearly, you should see that there's exponents and there's subtraction or addition involved in each one. And on the left, we're doing things inside the parentheses first, and then doing the exponent. And on the right, we are doing exponents on each piece and then doing the subtraction or the addition. And so a question would be, well, does it matter what order you do them in, or do you get the same thing all the time? And hopefully you should have seen that, no, you definitely don't get the same thing. So the 5 minus 1 is 4, 4 squared is 16. But if you do 5 squared and 1 squared, and then subtract, you don't get 16, you get 24. All right, similarly here, 125 and 65. Here, that's a 5 when you add negative 2 to 7. Remember, squaring a negative, it does come out positive, so that would be plus 4 and 49. So those are not the same, and these guys might need a calculator. Here, 5 to the 5th power is actually 3125. But if you do these guys to the 5th powers, you get those, and you definitely don't get 3125. Okay. Yeah, we're going to go to the next side. So here are a bunch of expressions, pair in each row. And turning this kind of thing into this sort of thing is something that people often try to do. And the question would be, well, are those two legitimately equal to each other or not? All right, when we've got variables in here, can you manipulate like that? Can you do that algebraic change or not? So, in the table here, if we think about them, are these always equal to each other? Like no matter what number goes in for x, are they always the same or are they different sometimes? All right, so just to show you the first one here to get us started, um, are those always the same? Well, to justify that takes some work. To disprove it means we can just find a counterexample. That is an actual number you can put in for x where those two things don't come out the same. And in fact, if you flip back to the previous page, we did exactly those computations with a 5 put in for x. So are these two things always equal? Well, no. To be real specific, for one example, they are not the same when x equals 5. And in general, I mean, x equals 5 isn't the only one. For most numbers that you put in for x, those don't come out the same. Now, it doesn't mean they always come out different. You can find numbers where it does work. In fact, if you put a 1 in for x, you'll get 0 for both of them, and they will be equal. But in general, they're not. All right? They're not equal for everything you could put in for x. In fact, they're not equal for most of the stuff you can put in for x. This is just one specific example that proves that these are not the same. And so that's what we call a counterexample. So if you go through the rest of these and compare them to the previous page, well, actually the next one, nope, on the previous page we had a 4 in for x basically and didn't come out the same. For this one we had a 7 in there for x and they didn't come out the same. And here's one, now it's got two variables, x and y, and actually that's the kind of thing we just computed on the previous page with a 2 in for x and a 3 in for y. So no, not equal. All right, so the even broader question would be something like this equation. This would be a general distributive property for exponents, if it actually works. Can you go from this to this? That would be convenient and it would be simple, but that doesn't mean it works. And in fact, these are all examples of this kind of thing where things definitely don't work. That is not a true equation. It's the kind of thing that I'm hesitant to even like put before you because I'm afraid you'll remember this and think, oh yeah, I can do that. But no, those guys are not equal to each other. You cannot do that. Exponents don't distribute is essentially what we're saying. And so yeah, all of these rows up in the table are all counter examples to this sort of thing. This would be the example where we have a 5 in for n specifically, and they don't come out the same when you have a 2 in for x and a 3 in for y. All right. So just to summarize, and that's how short this exploration is, suppose we're trying to figure out whether some sort of algebraic manipulation is legitimate. Can we really do this? You've got like x's and maybe y's or other variables, and you're wondering, can I do this thing? Can I combine these x's? Can I distribute this thing? Can I do something? One way you could always test that kind of thing is to put some actual numbers in for the variables and see if the two things that you think might be equal actually are. All right, that's like asking this question up here. Are these two guys always equal to each other? Can I just turn this into this? And one way to check that for yourself is to try some actual numbers in for x. And we saw that if you put a 5 in for x, these don't come out the same. So you should not turn one into the other. All right, so what if you try some numbers and it does work, though? Because like I said, you could put a 1 in for x and these would be equal to each other. You could put a 0 in for x and these two would be equal to each other. So if you try some numbers in for variables and it works, can you use that equation? Can you make that change? And well, no. Just because you found an example that it works for doesn't mean it's going to work for all the numbers that might go in for the variables. You just showed that it works for the specific numbers you chose, not for anything. All right, so what you're really looking for when you plug in some numbers is to see if things fail. So if you try some numbers in the variables and it doesn't work, then you have found a counterexample and you should not use that equation. So you should not go back and forth between these two guys because they are not equal to each other in general. You can find lots of numbers for x and y and n where these guys are not equal, so you should not turn one of those into the other. So that's the idea. So testing out with some numbers doesn't prove something works, but it definitely can prove that something doesn't work. And that's what a counterexample is. All right, and that's all of this exploration.